Having given a number of key definitions, we are now ready to look at how water flows. The motor driving flow is obviously energy, and not surprisingly, flow goes from places of high energy to those of low energy. The energy of a given water mass depends on compressibility, its vertical position above a reference level, and on the velocity with which it moves. These factors are quantified by the Bernoulli equation. The Bernoulli equation defines the amount of work needed to bring a given amount of water to its present state from a reference initial situation. Normalizing for the mass, we obtain H, which is the hydraulic head, usually referred simply to as head. This is the key word you need to remember. A further simplification can be obtained observing that the velocity of water flow in general is low, and therefore the last term of the equation can be neglected. This is the equation one can use to determine the hydraulic head of a water body. Let us look in some more detail at the meaning of a head, first considering only one well in a static situation where no flow takes place. When you dig a well, water will enter the borehole and will reach a level equal to that of the surrounding water table. We will call Z top the height of the water level with respect to a reference horizon, which is also indicated in the figure. Using the head equation and assuming that the pressure at the top of the water column is in the well can be neglected, you can see that the head is equal to the height of the water level with respect to the reference horizon. One can also determine the pressure inside the water column into the well. At each point, it will be equal to the depth of the point with respect to the water level times water density and gravity acceleration. Let us now look at the situation with two wells. Using the rules mentioned above, you can clearly see that well A has a head larger than that of well B. If possible, water would then tend to flow from A to B. The pressure at the bottom of the two wells depends on the height of the well itself. In the case shown in the figure, the pressure at the bottom of well A is larger than that of well B. Determining the head difference between water bodies and thereby predicting the direction of flow between them is crucially dependent on the establishment of a common reference level. In small regions, this is relatively easy. In larger areas, this is much more complicated. This is surely the case for the Netherlands, but it is a very important one, as more than 30% of the country is below sea level. Here, engineers have defined a reference level called NAP, and this is of crucial importance to predict if water will flow, for instance, towards or out of the polders. A very precise definition of the NAP is key to keep our feet dry. Now that we have the motor, we look at the flow. The two wells 1 and 2 shown in the picture have different heads, and water will flow from 1 to 2. Discharge across the layer is described by Darcy's law, which we have already seen while discussing petroleum geology. The discharge is proportional to the head difference and to the hydraulic conductivity, which is a property of the porous medium. A useful parameter is the specific discharge, which is the discharge normalized by the surface across which the fluid flows. The specific discharge provides a description of the average velocity of the fluid, water in our case, across a unit surface. What one extracts from the equation, however, is only an average velocity. In reality, water will flow only through the pores of the rock and not through the entire section. A more correct description of the system needs to be done, which includes also the connected porosity of the rock. Real velocities will then be significantly higher. Darcy's law has some significant limitations which should not be forgotten. It is valid for non-turbulent flow and for systems which are characterized by one density, always constant. The key lithologic parameter in Darcy's equation is the hydraulic conductivity. Looking at the table shown on the slide, you see that conductivity values for different types of sediments and rock can vary by orders of magnitude. Correct predictions are challenging, but of great importance. Always remember that one value is generally not enough. Rocks at the scale of water reservoirs are highly heterogeneous, laterally and vertically. We have seen some of these issues while discussing petroleum geology. In the summary slide, you see unconfined and a confined aquifer. Aquifers and aquitard have very different permeabilities, and therefore the rates at which water will flow are also very different. The numbers show the typical time needed for waters to flow from the surface to a specific place. Huge differences. When tapping in confined aquifers, you might be drinking fairly old water indeed. More will follow.